Welcome back. Today, we are completely changing how you look at the literal ground beneath your feet. It's so easy to just think of the Earth as a giant static rock floating out there in space. But actually, that couldn't be further from the truth. Our planet is essentially a colossal, constantly churning machine. It's a dynamic engine of continuous creation and destruction. And in today's explainer, we're going to deconstruct exactly how the whole thing works. Okay, here is our roadmap for today. We'll start with the Earth's endless battle, then meet the tectonic plates, explore the boundaries where they clash, uncover the hidden driving force, and wrap it all up with a massive case study on the Himalayas.
Starting right off with Section 1, the Earth's endless battle, a literal planetary tug-of-war.
Imagine an epic battle happening every single second on the surface of our planet between two totally opposing forces. On one side, you've got exogenic forces. Think of these as the external forces from up in the atmosphere, like wind, rain, and ice. Their entire goal is degradation, which is basically wearing down mountains and high points through erosion, and aggradation, which means filling up the low basins. Basically, they just want to smooth everything out. But, fighting relentlessly against them, we have endogenic forces. These are the internal forces originating from deep within the Earth, and their job is to continuously elevate or build up parts of the surface from the inside. So it's this endless, ongoing war. The outside is trying to flatten things, while the inside is pushing things up.
Here's the crazy part about that battle. Without those internal, endogenic builders constantly working, our planet would completely lose the war. The external weathering processes would totally even out all of our planet's relief variations. Without that internal engine pushing land masses up, weather and erosion would just wear everything away until Earth was nothing more than a flat, featureless rock. But obviously we have towering mountains and incredibly deep valleys all around us, so those internal forces are clearly putting up quite a fight.
Moving to Part 2, meet the tectonic plates, the gears of the Earth's machine.
Now that we understand the battle itself, let's zoom in and identify the literal gears driving those internal forces. But before we name the specific players, we got to define the playing field, right? And that is the lithosphere. The lithosphere is the rigid outer layer of the Earth. It's made up of the crust and the very top part of the mantle. And what's absolutely fascinating is how much the thickness varies. Underneath the oceans, it might be a relatively thin 5 to 100 kilometers thick. But under the continents, it can reach a staggering 200 kilometers in thickness. This massive, irregularly shaped slab of solid rock is exactly what makes up our tectonic plates.
You can think of these tectonic plates as giant puzzle pieces moving horizontally across the asthenosphere, which is a hotter, much more fluid layer of rock right beneath them. You've got the major heavyweights. We're talking the gigantic Pacific plate, the North and South American plates, Africa, Eurasia, and the India-Australia-New Zealand plate. But then, wedged in between those, we also have these fascinating minor plates, like the Cocos and Nazca plates off the coast of the Americas, or the Arabian plate. Together, the whole shebang forms this dynamic, shifting, fractured shell entirely encasing the Earth.
Section 3. Boundaries. Let's look at the friction points where these plates actually clash. Well, when you have a bunch of continent-sized puzzle pieces shifting around on a sphere, they're definitely going to bump into each other. And at those friction points, a few different things can happen. First up are divergent boundaries. This is where plates literally pull away from each other. And when they do, entirely new crust is generated to fill in that widening gap. Second, we have transform boundaries. This is where plates slide horizontally right past each other. This happens along planes called transform faults, which usually sit perpendicular to mid-oceanic ridges. In a transform boundary, crust isn't produced, and it isn't destroyed either. The plates just aggressively grind right past one another.
But at convergent boundaries, things get way more intense and a lot more destructive. This is where crust is actually destroyed because one plate dives directly underneath another one. We call that specific spot a subduction zone. And this dramatic collision can play out in 3 distinct ways, depending on who's crashing into who. It could be an oceanic plate diving beneath a continental plate, 2 oceanic plates crashing together, or 2 absolute behemoth continental plates colliding head-on.
Now you're probably wondering, if this movement is happening right now, how do we even know? How on Earth do we measure a planetary drift that's moving that incredibly slow? It's actually genius. Scientists do it by reading the ocean floor. They analyze strips of normal and reverse magnetic fields that run completely parallel to the mid-oceanic ridges. It acts almost like a giant geological tape measure recorded right into the rock, allowing researchers to track historical plate speeds with unbelievable precision. Sometimes it shows these massive plates moving at the exact same speed that your fingernails grow. Wild, right?
Part 4. The hidden driving force. Let's step inside the engine room.
So we know the plates move, we know how they violently interact at their edges, and we can even measure their speed. But what is the actual primary driving force behind this constant world-shaping movement? It's a massive question. Arthur Holmes was one of the first to really tackle this back in the 1930s, and his groundbreaking ideas ended up deeply influencing Harry Hess and his later discoveries about how the seafloor spreads.
The answer they eventually pieced together lies deep underground, in the hot, softened mantle rock right below those rigid plates. It turns out, this material actually moves in a huge, circular manner known as convective flow. And what fuels this immense planetary boiling pot? Just unbelievable amounts of intense heat. Specifically, heat coming from two main internal sources, radioactive decay and the residual heat left over from the very formation of the Earth itself billions of years ago.
Let's break down exactly how this convection cell works step by step. First, that intense internal heat warms the mantle material, which makes it less dense, causing it to slowly rise up toward the Earth's surface. Second, as it gets near the top, right underneath our rigid lithosphere, it spreads out horizontally and starts to cool down. Finally, step 3, because the cooled material is now heavier and denser, it naturally sinks right back down into the deeper depths of the Earth. This continuous, repetitive cycle of rising, spreading, cooling, and sinking creates an immense convection cell, and this incredibly slow flow of softened mantle acts exactly like a giant conveyor belt, just dragging the tectonic plates along for the ride.
Which brings us to Section 5, a case study on the Himalayas, the grand finale of the Indian Plate.
To truly wrap our heads around the unbelievable power of this internal engine, let's look at the Indian Plate's high-speed, geologically speaking of course, collision course. If we rewind 225 million years ago, the Indian Plate was completely separated from the Asian continent by a vast body of water called the Tethys Sea. Fast forward to about 60 million years ago, and the plate's incredibly forceful movement caused a monumental outpouring of lava, forming what we now call the Deccan Traps. This intense volcanic event went on for a really long time. Then, the main event. Around 40 to 50 million years ago, the Indian Plate violently slammed right into Asia. That subduction zone along the Himalayas forms the northern plate boundary. But because this was a continent-continent convergence, literally two unbelievably thick, heavy slabs of rock smashing head-on into each other, something incredible happened. The crust had nowhere to go but straight up. This single collision initiated the rapid uplift that created the highest mountain range on Earth. And the craziest part? Because the internal engine of the Earth is still running, that pushing hasn't stopped. Mount Everest is technically still growing. So let's leave off with this thought. If this hidden earthly engine of destruction and creation is constantly being driven by deep convection currents, and if it's still churning right now as we speak, what new landscapes, what towering future mountains or completely new oceans are slowly being built beneath our feet today? The ground you stand on isn't a permanent fixture, it's just a temporary snapshot of a planet in constant, beautiful motion. Thank you so much for diving into the dynamic Earth engine with me today. Keep exploring, stay curious, and I'll catch you in the next explainer.